In this video, we're going to discuss the section 2.1 population models, but this is part two. In our first part one video, we discussed the first 3 pages of the notes, and we're going to finish the last 3 pages of the notes in this video. But first, before we get to the new material, let's just recall what we learned in the previous video. We introduced the general population equation, which is given right here at the top of page 1. The general idea here is that the rate of change of the population with respect to time is just the birth rate, which is a function of time, minus the death rate, a function of time, times the population P. All right, so this is the general population equation. And then we introduce what's known as the logistic equation, which is really just a very specific form of this general population equation. So let's look down at that. We did problem 10, which illustrated the general population equation. And then on page 2, you'll notice what I have highlighted and circled. We are making the assumption that the birth rate is a linear decreasing function of P. So we're writing this as beta naught minus beta 1P, and that becomes our birth rate. Our death rate right here is just constant. So it's still the general population equation in that we're taking beta minus delta times P, but we're writing it in a very particular way. And typically speaking, what we'll do is we will keep 1P factored out front and look at that as a product of 2 linear factors. The integration technique that we'll be relying on to solve these types of problems is integration via partial fraction decomposition. So then at the end of part 1, we worked through problem 26, which again was just illustrating that general population equation, or excuse me, the logistic population equation. And we have another example here, problem 23 from the text that's going to work with that logistic equation. So let's see, we have as the salt dissolves in methanol, the number X of T of grams of salt in a solution after T seconds, okay, so time is in seconds, satisfies that given differential equation. Part A, what is the maximum amount of salt that will ever dissolve in the methanol? So at this point, I'd like you to think back to how we found maximum and minimum values way back in Calc 1. Typically, when we were given a function to find those optimizations, we would take the first derivative, set it equal to 0 to find those critical points, and then we would test and see if each critical point was a maximum, a minimum, or neither. So again, we were setting the derivative equal to 0. Now that we're in differential equations, we already have the derivative solved for us. So finding when these maximums occur is going to be quite a bit easier. So I'm just going to make a note here that the max occurs when the derivative is equal to 0. So I'm just going to take that right-hand side and set it equal to 0. And then if I factor out an X, that leaves me with 0.8 minus 0.004x. And then I can set each of those factors equal to 0. So I get 0 and 0.8 over 0.004, which comes out to 200. So if you look at these, remember X of T is the number of grams of salt in the solution, and we're trying to maximize the amount of salt. So certainly 0 would not be a maximum. That's just an extraneous point there, a different critical point. But we do have 200 grams as our other critical point, which is going to serve as our maximum amount. All right, so no need to solve the differential equation in order to optimize it. That's one of the nice things about working with the derivative. All right, but part B is going to ask us to solve this in some way. It says, if X equals 50 when T equals 0, how long will it take for an additional 50 grams of salt to dissolve? So we have an initial condition here that X of 0 equals 50 grams. And the question is, what does T equal so that we have diluted an additional 50 grams? So 50 on top of 50 gives us 100 grams. All right, What I want to note here, and I'll even write it for in red, they do not ask us to solve for x of t. No need to solve explicitly for the solution x of t. I feel like quite often we're so programmed to work through the problem in full and get the general solution, but if they don't ask you for it, there's no need to go through that extra work. So just keep that in mind as we're working out this problem. All right, so let's go ahead and take a look here. Recall that our differential equation is dx dt equals 0.8x minus 0.004x squared. And just to make things a little bit cleaner, I'm going to go ahead and factor out a negative 0.004x because I don't like dealing with all of those decimals everywhere. So if I factor that out, that's going to leave me with an x minus 200. And now I'd like to separate variables. I'm going to move all of the x terms to one side. Specifically, I'm going to just take the green highlighted area to the left. So I have dx over x times x minus 200. And then I'm just going to leave that constant negative 0.004 and then kick that dt differential over. All right, so here again, what we see is we have the integral of a rational function on the left-hand side, both of which those factors are linear. So I'm going to go through the method of partial fraction decomposition. Since they're both linear, I'm just going to tack an a and a b on top. I'm putting a on top of x, but you could put a on top of x minus 200 if you want. So your a and b might look different than mine. And I'd like to solve for a and b so that I can integrate directly. So I am going to equate the integrands. So dropping the differentials. And then to knock out all of the fractions, I'll go ahead and multiply through by the common denominator, which is x times x minus 200. So multiply that entire equation through. That gives us 1 equals a times x minus 200 plus bx. All right, so here's our setup. Again, this equation that I just wrote must hold true for all x values. So I can choose some particular x values that'll make it easy to solve for a and b. So first of all, let's choose x equals 0. That allows the b term to drop out. And so I would get 1 equals negative 200a, or a equals negative 1 over 200. And then similarly, if I choose the root of the other factor, namely 200, the a term drops out and I get that b equals 1 over 200. All right. So now what I'm going to do is I'm going to plug all of this back up into the integral up above. So where I see a and b up here, I'm going to plug in these a and b values. So I have the integral of negative 0.004 dt equals, I'm going to just factor out that 1 over 200 and write it as negative 1 over x plus 1 over x minus 200 dx. Okay, so now we can integrate. As always, I just want to note here that if you feel uncomfortable, you can run through a u substitution here for x minus 200. Your du is going to become your dx. So this is just going to become a natural log. But had there been some other coefficient in front of this x, whether it be a negative 1 or something other than that, you would need to make sure that you don't just blindly throw a natural log in front. Make sure that nothing is going to pop out due to a u substitution. So that being said, let's go ahead and continue. I have a negative 0.004 t plus some constant of integration equals 1 over 200, the natural log of x plus the natural log of x minus 200. All right. And then what I'm going to do here is I'm going to take this 200 and I'm going to multiply it over to the other side. I will absorb it into the C. So if I do that, 200 times 0.004 is going to get me back to that 0.8. And here you could write 200C, but that's just another constant itself. So I'm going to absorb it. And then I'm going to use logarithm properties to say I have the sum of two logarithms. So you multiply them together, but actually it's a difference, right? Because we have that negative. So that absolute value of x is going to go on the denominator. So I have the natural log of x minus 200 over x. Now here again, we discussed that, yes, we could solve explicitly for x, but there is absolutely no gain in doing so. And that's what I wrote up in red. So I'm going to just make a note that I am not solving for x. Could I? Sure. Is it going to take a lot of time? Yes. And am I going to gain anything from doing that? No, I'm not. So I'm just going to leave it exactly like this. And next I'm going to impose my initial condition. So recall that x of 0 equaled 50 grams. So let's plug that in here. On the left-hand side, I get C. On the right-hand side, I get the natural log of 50 minus 200 over 50. So, whoops, that would be negative 150 over 50 is negative 3, but we get the absolute value here. So I get the natural log of 3. Plug that back in to your equation above. So I have the natural log of 3. And then my right-hand side remains. And then remember what we're looking for. What is the value of t so that x of t equals 100? So I'm going to leave my left-hand side as is. I'm trying to solve for t. And on the right, I'm going to plug in 100 for x. All right, so I get a negative 100 divided by 100 is negative 1. The absolute value makes it positive 1, but recall that the natural log of 1 is 0. So what I get here is t equals the natural log of 3 over positive 0.8. And this comes out to roughly 1.37 seconds. So in a short amount of time here, 1.37 seconds is how long it will take for an additional 50 grams of this salt to dissolve into the mixture. All right. So on the next page here, we want to introduce some more definitions that'll be used throughout the section. At the top here, the book is just giving you the solution to the logistic equation. Now, I am skipping the steps going from the DE to the solution, but it's exactly what we just did here in this previous problem. You would separate variables, then you would recognize that your side with the p's would have a rational integrand with linear factors, separate by way of partial fractions and integrate and then solve explicitly. So I'm going to forego that proof there, but it's exactly the same approach that we did up above. And the book is noticing something. It says, what happens to this population solution as time marches on to infinity? And so they plug in for P of t, the general solution. And as t goes to infinity, what happens to this term? So if you recall the natural exponential function, here's what e to the negative t looks like. So assuming that both k and m are positive values, we see that that term goes to 0. And so all that lives on is the numerator and this p naught, which is what they wrote down in the next equality. Those p naughts, that's the initial population, those can cancel, and we just get m. So M is called the limiting population or the carrying capacity. So if you think of this in terms of the human race, for example, the resources on the planet Earth can only sustain so much life. If we had too large of a population, we may run out of drinking water or food or spaces for humans to live. And so there is a maximum capacity at which the population can survive. That's exactly what we're finding here is this M value. Similarly, we want to take a look here at another situation. We have this definition that says in the case of a constant death rate and birth rate proportional to P, the logistic equation becomes this equation. And so you'll notice what has happened is the roles of P and M have switched, right? So instead of M minus P. In this case, M is called a threshold population. We say that doomsday occurs if the population explodes, all right? So doomsday is when the population tends to infinity, and extinction is when the population goes to zero. So I think a lot of times doomsday and extinction get conflated. When people hear the word doomsday, they just think everyone's going to die. And while doomsday is very doom and gloom, we don't want our population to go to infinity because then we cannot sustain that. I just want to point out here, doomsday is when it heads to infinity, extinction is when it heads to zero. There's a distinct difference between those two. So I'd like to finish this section off by working with an example that works with doomsday in particular. All right, problem 13 from the text. Consider a prolific breed of rabbits whose birth and death rates, beta and delta, are each proportional to the rabbit population P of T, where the birth rate is higher than the death rate. Oops, that alpha should be a delta. All right, so we want to show, first of all, that the population can be given by this expression for some constant K. And then we also want to note that the population tends to infinity. In other words, doomsday is occurring as T approaches this constant value. All right. So this is an example where they're giving you the answer. There is going to be no answer in the back of the book because they're telling you what the solution is. They just want you to deduce it. All right, so let's go ahead and take a look here. Let's set up our differential equation first of all. We have that the birth and death rates are proportional to the rabbit population. So let's set up some proportions here. Beta is equal to K times P, where K is some constant of proportionality. Now, what I don't want you to do is use the same constant of proportionality for the death rate. You can't assume that the proportion is exactly the same. For example, if the birth rate is double the population, you can't assume that the death rate is double the population. It might be some other constant in front. So what I'm going to do is I'm going to put a little subscript 1 here for my first constant of proportionality. And then let's set up the death rate. Delta is K2 times the population. And then just introduce those 2 new variables. We know what beta and delta are. They were defined above. We know what P is, but we have not introduced K1 and K2. So for constants, K1 and K2. All right, so now let's go ahead and set up our differential equation. Remember, the general population equation is beta minus delta times the population. So in this case, that would be K1P minus K2P times P. And then here again, we can factor out this P since it was proportional in both terms and write this as K1 minus K2 P squared. So we have our population equation, and thankfully, since we were able to factor out all of the P's, we won't need to use integration by way of partial fractions. So let's separate variables, 1 over P squared dP, and then I'll just leave my K1 minus K2 constant over here with the dt. So let's go ahead and integrate. This becomes a negative 1 over P equals K1 minus K2t plus some constant of integration. So if we solve explicitly for P of t is equaling -1 over K1 minus K2t plus C. All right, now when we look up at the solution that we're supposed to get, notice that they write it in terms of some generic initial population. So we would like to kind of flesh that out. I'm going to say that let the initial population P of 0 be denoted by P naught. And so if I plug in 0 for T, let me highlight here, then what that does is that gives me P naught equals -1 over C, because that entire bottom term, K1 minus K2T, goes to 0. So I conclude that C is equal to -1 over P naught. All right, so now let's go ahead and plug that into our P of T solution. And if we look up above, this still isn't quite what we're looking for. So to remedy that, let's go ahead and multiply the numerator and the denominator by a -P naught, and that'll simplify things. So the top becomes P naught, the bottom becomes a -P naught K1 minus K2T plus 1. And then we're almost there. The only difference here is that they have renamed their K1 minus K2 into just some general K. So if we rename it, we can say that this is P naught over 1 minus K P naught T for K equal to K1 minus K2, which was a constant. Check. All right. So we have done the first part. We have shown that the solution to this differential equation is given by P naught over 1 minus K P naught T. So then there's one little thing here that they noted, which was talking about doomsday. So I will just kind of flesh that out a little bit. Note that the population explodes when what happens? So what I know is this numerator is just a constant. It's whatever the population started out as. So I have a constant on top and then some expression on bottom that depends in time. How can you take an expression that is a constant on top and then something else on bottom and make it tend to infinity? The numerator cannot go to infinity because the numerator is a constant. But if the denominator tends to 0, division by a really small number ends up making the overall fraction blow up. So we approach doomsday as the denominator 1 minus K P naught T approaches infinity, approaches 0. And so if we solve for T here, we would have -K P naught T approaches -1, or T approaches +1 over K P naught. All right, so we just proved that in fact doomsday does occur at as T gets closer and closer to 1 over K P naught. All right, let's take a look at part B here. It says, suppose that the initial population is 6 and that there are 9 rabbits after 10 months. So I'm just making a note here that T is in months. I just made that decision. If you wanted to do it in years, then you could write it as 10 over 12 inside. All right, so the question is, when does doomsday occur? All right, so we already said that doomsday occurs when T approaches 1 over K P naught. And we now know what P naught is, right? That's 6. So the only thing we're missing here to determine when doomsday occurs is the K value. So what we're going to do is we're going to use these two initial conditions that we were provided with here in part B, plug them back up into our solution in part A to solve for K. So our P of T function plugging in for P naught is 6 over 1 minus 6 KT. And then let's go ahead and just plug in P of 10. So P of 10 is 9, but that is 6 over 1 minus 60T. So if I multiply both sides by 1 minus 60T, I get 1 minus 60T equals 6/9 or 2/3. So 1/3 equals 60T, or T equals 1 over, oops, darn it. These T's should be K's, so let's correct those. I'll write them in red. I plugged in 10 for T, but I just acted like it was K. So let me fix that in red. This should be K, K, K. And then same right here. All right, there we go. So K equals 1 over 180. All right, so we have our K value, and now we're home free. Remember, doomsday occurred as T was approaching 1 over 6K, which is 1 over 6 times 180, 1 over 180, which is 1 over 1/30th, or 30. Now keep in mind what your time was in respect to. This was 30 months. So this sure is a prolific breed of rabbits here. After only 30 months, it will have reached doomsday. It will have reproduced so much that its population is not sustainable. All right, this concludes our notes on 2.1 population models. And up next, we'll be talking about section 2.2 equilibrium solutions and stability.